Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to today's lecture on biochemical reactions. In the previous lecture, we talked about a specialized type of reactions which were called the combustion reactions. Today, we will talk about biochemical reactions which are specifically useful for people working on biotechnology and bioprocess industries. So, the start of the lecture, we will discuss what enzyme reactions are and how we can use them for performing material balances with respect to enzyme reactions. What are enzymes? Enzymes are proteins that catalyze biological reactions. These enzymes are very highly specific, and these enzymes can actually increase the rate of reaction very significantly. The rate of enzyme catalyzed reactions are usually much higher than the rate of the same reactions which can be catalyzed by non-biological catalysts. The reaction conditions which are used for enzymatic reactions, the conditions such as pH, temperature, are usually mild because you do not want the enzyme to get denatured. The enzymes are very sensitive because extreme conditions in temperature or pH can easily damage or denature these enzymes, and for this reason most of the times reactions with respect to enzymes happen at mild conditions which are closer to natural conditions. Enzymes are named with a certain specific method. So, initially enzymes were given non-descriptive names such as trypsin, pepsin, etc. And over a period of time, people realized that this was not a very useful way of naming enzymes. So, they started having a new nomenclature where they added A's to either the substrate or the reaction that is being catalyzed by the enzyme. So, this gave a little more clarity on what the enzyme did. An example like lipase, lactase or cellulase, you know that it is acting on lipids or lactose or cellulose. If the name was an alcohol dehydrogenase or a glucose isomerase, we knew that it performs a dehydrogenation reaction or an isomerization reaction. This gave some information about what the enzymes were. This was further improved in 1964 when a new systematic scheme was formed by the International Enzyme Commission. So, the enzymes were classified under 6 major categories, and within that there were sub-classifications. We will not go into the sub-classifications, but we will give the 6 major classifications which were defined based on the reaction they catalyzed. So, the first would be oxidoreductases. These enzymes catalyzed oxidation and reduction reactions. Example would be dehydrogenase or oxidase. You also have transferases, which are basically enzymes which help in transferring a functional group from one substance to another. Example would be kinase and transaminase and so on. You have hydrolases which form two products from a substrate by hydrolysis reactions. Lipase and amylase are examples where hydrolysis happens. Lyases are enzymes which basically catalyze non-hydrolytic additions or removal of groups from a substrate. Example would be decarboxylase. You have isomerases which catalyze the isomerization reaction. Isomerase and mutase are examples. And you have ligases which catalyze reactions which join two molecules by formation of new bonds to form a final product. Example would be a synthetase. So, these are the 6 major classes of enzymes, and within these there are many subdivisions. We will not get into the details of that, those are covered in basic biochemistry courses. If you are interested, please refer to some fundamental biochemistry book which will give you a better classification and give you all the details about the subclasses for enzyme classification. How do enzymes work? Enzymes are like any other catalyst. So, what do catalysts do in general? You have the free energy of the reactants and the free energy of the products. For the reactants to be converted from their free energy state to the product's free energy state, they actually have to go through a hill which is shown here. This hill is the activation energy which the reactants have to have so that it can get converted to form the product. So, when the enzyme is present or any catalyst is present, this activation energy is reduced. So, you see in the enzyme catalyzed reaction that the hill is smaller. This gives you a lesser activation energy, thereby making the reaction more spontaneous than what it would have been if no catalyst or enzyme was present. So, this is how enzymes work. Now, when we perform enzyme based reactions, we have to understand how the kinetics of the enzyme works. So, there are some simple enzyme kinetic models which help us to understand how enzymatic reactions happen. So, let us assume this particular simple reaction where a substrate is converted to a product in the presence of the enzyme. So, the simplest reaction equation for that would be S gives P in the presence of E, the enzyme. So, the rate of reaction V for this can be given in terms of the change in concentration of the substrate or the product. So, that would be given mathematically as V equals minus ds dt or V equals dp dt, where minus ds dt is the rate of consumption of substrate S with respect to time, and dp dt would be the rate at which product is produced with respect to time. So, when you actually try to understand the effect of substrate concentration, product concentration and enzyme concentration, you get this particular setup. What you have here is results from multiple experiments where different concentrations of substrate and enzymes were used and the initial rate of the reactions were measured. So, this was plotted as initial rate V versus substrate concentration S. So, this particular plot follows the saturation kinetics. As you can see here, you have two different curves, one for an enzyme concentration E and the other one is for an enzyme concentration of twice of E. So, what you see here is as the concentration of enzyme increases, the maximum rate which can happen has actually increased proportionally. So, let us look at what are the parameters here. Other than the maximum rate, which is Vm, we also have another term called Km. Km is a constant which is the dissociation constant. So, Km gives us an understanding of the affinity of the enzyme to the substrate. So, the lower the Km, higher is the affinity. If we were to look at this particular setup, what we see is when the substrate concentration is low, the reaction rate is proportional to the substrate concentration, which is what you see in the initial phase where it is almost a straight line in the initial stage when the substrate concentration is low. As the substrate concentration increases, what you see is the reaction rate does not depend on the substrate concentration anymore, which is what you see here. So, what you see here is the reaction rate has not changed significantly, although the substrate concentration has been increasing tremendously. This is because it follows a zero order reaction when the substrate is in excess. And you also see that the maximum reaction rate Vmax or Vm is proportional to the enzyme concentration. So, why does the reaction follow this kind of a setup? So, what you usually have is the enzyme reaction as given here. Enzyme and substrate react to form the enzyme substrate complex using a reversible reaction, and this then ends up producing the enzyme and the product. So, the product leaves and the enzyme remains in its native state. So, this is the enzymatic reaction. So, when the substrate is present at low concentrations, then the number of active sites which are present in the enzyme becomes the limiting factor. So, you have all the substrates attached to an active site, and as you increase the substrate concentration, more substrates attached to the active site, thereby increasing the rate of the reaction proportionally to the substrate concentration, giving you a first order reaction. However, when the substrate concentration exceeds a certain number, what will happen is all the active sites present in the enzyme are occupied with substrate molecules. This means adding more substrate will not hasten the rate of the reaction. So, that is when the rate of the reaction reaches a maximum value, which is Vmax or Vm. So, now to increase the rate of the reaction after all the active sites are filled with the substrate molecules, we can add more enzyme, thereby increasing the number of active sites. As the active sites increase, you would have the rate of reaction also increasing, thereby the maximum velocity or the maximum rate also increases. So, this explains why we see a first order reaction when the substrate concentration is low, and a zero order reaction when the substrate concentration is high, and we see an increase in Vmax or Vm when we increase the enzyme concentration. So from this equation we can derive a mathematical model called as the Michaelis-Menten equation. This is a mechanistic model for enzyme kinetics, and the equation is written down as V equals Vms divided by Km plus S. So the terms V represents the velocity or the rate, Vm represents the maximum rate which can happen for the reaction, and S represents the substrate concentration, Km is the Michaelis-Menten constant. So amongst these things, the Michaelis-Menten constant, as I already mentioned, represents the dissociation constant and thereby talks about the affinity of the enzyme to the reaction to the substrate, and you also have Vm which accounts for the enzyme concentration. So Vm has an enzyme concentration or the initial enzyme concentration inbuilt into it, and Vm is proportionally varying with respect to enzyme. So this can actually be derived, however the derivation for this equation is outside the scope of this course, and you can look up any biochemical engineering textbook where you would be able to see the derivation, and you can go through them as for your own exercise. Now from our material balance perspective, let us consider a reactor where enzymatic reaction is happening. So we will account for a CSTR, which is a continuous stirred tank reactor in which an enzyme reaction that follows Michaelis-Menten kinetics is happening. So we will assume that it is an ideal CSTR, which means the reactant contents are well mixed. This means the concentration of all the components are the same in any part of the reactor. This would mean that the concentration in the exit stream is the same as the concentration inside the reactor. So under this ideal condition, what will happen is any feed which comes in will get instantaneously mixed well inside the reactor, thereby you will have uniform concentration throughout the reactor. As you are taking it out in the exit stream, the concentration in the exit stream will be equal to the concentration which is present at the exact outlet point inside the reactor, which will be the same as the concentration all over the reactor, thereby giving you a uniform concentration in your exit stream and your reactor. So let me explain to you with the diagram. As you see here, this would be a simple representation for a CSTR. If I have an ideal CSTR, the concentration of a component would be the same in all these points which I have marked. That is because it is a well mixed reactor. So this would also mean that the concentration at this point, which is where the exit is being drawn, would also have the same concentration as the concentration present anywhere else in the reactor. As this concentration is the same as what you see in any part of the reactor, the concentration in the exit stream will also be the same as the concentration inside the reactor. However, the concentration in your inlet can be different. As soon as it enters into the reactor, it will get well mixed and you will have a uniform concentration inside the reactor. So this is what an ideal CSTR represents. Now can you write a material balance for substrate for this reactor? Let us try to do that. So this represents a CSTR with all the parameters listed down. So here you have F, which is volumetric flow rate, so which would be in terms of liters per hour, and you would have S naught, which is the inlet substrate concentration. This can be in terms of moles per liter or grams per liter, and you have S, which is the outlet substrate concentration, again in terms of moles per liter, and you have Vr, which is the reactor volume, which would be in terms of liters, and V represents the rate of the reaction, and the units would be moles per liter hour. Now that we have all these parameters, let us start writing the balance equation for the substrate. we start with input minus output plus generation minus consumption equals accumulation. For the time being, let us not assume steady state. We will start writing all the equations and then we will cancel out terms which can be removed at steady state conditions. So, we are writing for the substrate balance. So, substrate is a reactant, which means there is no generation term, you only have a consumption term. So, you can remove the generation term. So, the input would be F times S naught. So, this gives us a unit of liters per hour times moles per liter, giving us moles per hour. So, the balance equation we are writing is for moles per hour minus F times S, which is the substrate concentration in the outlet stream, and these two will be of the same units. Now, you have to write a consumption term. So, we know the rate of consumption, which is V. So, this rate of consumption is given in terms of moles per liter hour, and we need the term to be in moles per hour, and this rate is with respect to the volume of the reactor. So, the number of moles of the reactant which is consumed per liter of the reaction volume per hour is the rate of the reaction given. So, to get the total number of moles which would be consumed per hour, we have to multiply this velocity or rate with the volume of the reactor, which is VR. This would be equal to the accumulation, which would be ds dt, rate of change of substrate concentration times VR, which would again be the volume, giving us the rate of change of substrate amount with respect to time. So, this would be the balance equation we start with. So, from here we can assume certain conditions such as steady state, and thereby at steady state you have ds dt equals 0. So, this implies the equation becomes Fs naught minus Fs minus Vr equals 0. So, dividing the entire equation by the volume of the reactor, we get F by Vr times S naught minus F by Vr times S minus V equals 0. From the Michaelis-Menten equation, we know that V equals Vm S divided by Km plus S. So, we can substitute this here to get F by Vr equals Vm times S, which is the substrate concentration leaving, divided by substrate concentration inlet S naught minus S times Km plus S. So, this equation can be derived using material balance equation. So, now we have the definition for F by Vr as the dilution rate. So, this is a term which is usually used for understanding and designing reactors. So, this dilution rate is equal to 1 by tau, which is the residence time inside the reactor. So, we can calculate residence time tau as S naught minus S times Km plus S divided by Vm times S. So, using this equation we can calculate the residence time for the reactor, and also we can calculate the volume of the reactor to design the CSTR for the required operations. Using these equations we can calculate tau, which is the residence time in the reactor, and also Vr, which is the volume of the reactor. Thereby we can help in designing the reactor. So, the simple material balance can help us in designing the volume of the reactor, which would be required for getting a certain level of conversion. Now, let us test our understanding using an example problem. So, here is the example problem. A substrate is converted to a product by the catalytic action of an enzyme. Based on the experimental data, the Michaelis-Menten parameters are measured as Km equals 0.03 moles per liter and Vm equals 13 moles per liter minute. What should be the size of the CSTR to convert 95% of the incoming substrate? So, let us assume the inlet substrate concentration is 10 moles per liter. with a flow rate of 10 liters per hour. Assume that CSTR is operating under steady state conditions. Let us go and solve this problem as we solve any other material balance problem. So, the first step would be to identify the basis. So, here we have been told that 10 liters per hour is the inlet feed of the substrate. So, we will take that as the basis. With that, we can write material balances which would be input minus output plus generation minus consumption equals accumulation. At steady state there is no accumulation, as we are writing a balance for the substrate, the generation would also be 0. So, this equation will come down to the same equation which we derived, thereby we will get F by VR as V max or Vm times S divided by S naught minus S times Km plus S. So, now that we have this equation, we have to calculate VR. So, VR or the volume of the reactor would be F times S naught minus S times Km plus S divided by Vm times S. So, let us write down all these values. We will get VR equals 10 liters per hour times 10 minus 0.5. So, we have 95% conversion, which means only 0.5 moles per liter of the substrate is leaving the system. So, you have the final substrate concentration as 0.5 moles per liter. So, this would be moles per liter times 0.03 K, which is the value for Km, plus 0.5 which is the S value, which would also be in terms of moles per liter, divided by V max, which is 13 moles per liter minute. So, we have the flow rates in terms of hours. So, we will convert this to hours by 60 minutes per hour times 0.5 moles per liter. So, now these liters cancel off and this mole cancels off, this mole also cancels off, and we have these 2 liters getting cancelled off and the hour terms getting cancelled off. So, finally, we get dimensions of liters, which would mean the volume can be calculated from here as VR equals 0.129 liters. So, this would be the volume of the reactor which is required for getting 95% conversion of the substrate which is being fed. With this, we come to the conclusion of the examples on enzymatic reactions. So, in the next lecture, we will talk about another class of biochemical reactions, which is cell growth. Until then, thank you and goodbye.